Most people think airplanes are designed to never fail, that every component must work perfectly, that every system has to function exactly as intended, that any failure in the air automatically means disaster. That belief feels logical, it feels safe, and it is completely wrong. Modern airplanes are not designed to operate flawlessly. They are designed to keep flying after something has already gone wrong. In fact, when an airplane leaves the ground, engineers already assume that parts of it will fail at some point. Not as a rare accident, not as an extreme scenario, as an expectation. That single assumption changes everything. From the outside, an airplane looks like a single machine. One fuselage, two wings, a tail, a few engines. It looks solid, rigid, almost invincible. But internally, an aircraft is closer to a living system than a machine. Hundreds of independent subsystems, thousands of components, each one with its own failure modes. And the plane is designed knowing that some of them will not survive forever. Let's start with the most obvious example: engines. Most passengers assume that if an engine fails, the flight is immediately in danger. But commercial airplanes are certified to fly safely with one engine completely dead. Not just cruise, take off, climb, divert, land. Pilots train for engine failures constantly. Simulators repeat it over and over. Checklists are built around it. Because engines are not considered perfectly reliable, they are considered replaceable. Bird strikes, ice ingestion, fuel flow issues, mechanical wear. Engines operate under extreme temperatures, pressures, and rotational speeds. Eventually, something will force one to shut down, and the airplane is built assuming that will happen. But engines are not the most important systems keeping a plane in the air. Wings are, and this is where reality becomes uncomfortable. Wings are not rigid structures. They bend, they flex, they move constantly. During flight, wingtips can bend upward several meters. This bending is not a sign of weakness, it is survival. A rigid wing would snap under load. A flexible wing spreads stress gradually across the structure. Flexibility is what allows wings to survive turbulence, gusts, and uneven lift. But flexibility creates another problem: control. So airplanes rely on hydraulic systems to move flight control surfaces. And here comes the next surprise. Aircraft do not rely on one hydraulic system. They rely on multiple independent ones, usually three. Separate pumps, separate power sources, separate routing paths, because engineers assume one hydraulic system will fail, sometimes two. The aircraft must still be controllable, even if power is lost, even if pumps stop working, even if parts of the system are damaged. And if all hydraulics are lost, there are still mechanical and aerodynamic methods to influence the aircraft. Not comfortably, not precisely, but enough to land. Now let's talk about computers. Modern aircraft are full of them. Flight control computers, navigation computers, engine management computers, sensor fusion systems. Computers make flying safer, but they introduce a new type of risk. Because software does not fail gradually. It works perfectly until it doesn't. There is no bending, no warning noise, no visible crack, just incorrect logic. That's why critical systems are often duplicated by entirely separate computers. Different hardware, different software, different teams, different assumptions. If one system becomes confused, another challenges it. Disagreement is safety. Now let's talk about pressure. An airplane is not just flying. It is constantly being pressurized and depressurized. Every climb, every descent. The fuselage expands slightly under pressure, then contracts again. Over thousands of flights, this cycling creates fatigue, not visible damage, microscopic damage, Tiny cracks form around rivets, seams, and joints. Engineers know exactly where these cracks will appear, not because planes are poorly designed, but because physics is predictable. So aircraft are designed with inspection intervals, component replacement schedules, strict fatigue limits. A plane may look perfect from the outside, but internally, it is aging with every flight. This is why airplanes are retired, not because they stop flying, but because the safety margin disappears. The structure can still hold, but engineers know something passengers can't see. The tolerance is gone. And here's where the paradox becomes clear. A plane is safest not when nothing is wrong, but when everyone assumes something will eventually be wrong. This mindset changes design. It changes training. It changes culture. Aviation does not aim for perfection. It aims for resilience. It assumes failure, plans for failure, practices failure. Pilots train not for ideal flights, but for broken ones. Checklists exist not because pilots are careless, but because humans are human. Memory fails, attention drifts, stress narrows perception. Checklists compensate for that. Now think about this. Every flight you've ever taken was completed successfully, even though parts of the aircraft were no longer new. Some systems had failed before. Some components had been replaced. Some tolerances were already consumed. And yet the plane flew. Because aviation safety is not built on hoping nothing goes wrong. It's built on expecting that something eventually will, and designing around that reality. That's why flying is statistically one of the safest forms of transportation ever created. Not because planes are flawless, but because failure is assumed from the beginning. So the next time you sit inside an aircraft at cruising altitude, remember this. Somewhere in that machine, something has already failed before. Something else will fail again, and the plane will keep flying. Not because it's lucky, but because it was designed to survive imperfection. Planes don't stay in the air because nothing breaks. They stay in the air because braking was expected and planned for. That is the real secret behind aviation safety.